Not the Hi, this is not the lecture. This is actually description of one problem that will be covered in the on the quiz on Monday. However, I cannot start this off with just the methods. I have to explain an application of where this comes from because it is actually important. And someone in class had pointed out that logs and exponentials were something new to them. So I want to explain what this is all about. And through an example. So today, children get letters in some school districts that tell the parents that their body mass index is too high. This is actually a excerpt from the CDC where they suggest that the student's BMI result, which is measured by the school nurse typically, that he or she might be overweight or classified with obesity. So notice that there's information that they provide in this letter. So I do know parents who have got this letter from home, and it's a stressful thing to get a letter like this. So what is body mass index? Well, it turns out that the definition of body mass index is weight divided by height squared. It's a measure of what I call in class adiposity, or body fat percentage. Because weight divided by height squared is closely related to percent body fat, we use weight divided by height squared as a proxy for body fat because body fat is actually hard to measure. So the question is, weight divided by height squared is really pretty accurate for being a proxy for percent fat for adults. But does it describe percent fat well for children? Does it accurately describe adiposity in children? Because if we're sending these letters home and they're stressful, believe me, they're stressful when you get a letter like that home about your child, we better be right. So I have for you here CDC data on boys age 8 to 25, and it's cross-sectional. So there's actually these mobile carts. The CDC does this throughout the nation. They go around the nation and they measure all kinds of things in people. And so these are children's data across the nation. And there's a collection of their body weight, their height, their percent fat, and a number of other things. And you see that this data is over here. I have the data here, a sample of the data, not all of it, but just showing you that the height is usually given to us in centimeters, and the weight is usually given to us in grams. But for me to use body mass index, I need weight to be in kilograms, so I converted it from grams to kilograms by dividing, and then I converted the centimeters by dividing by 100 dividing by 100 to get the meters. I just wanted to show you the translation for height in inches and weight in pounds so you can get an idea of how many pounds these children are in at least the sample I've shown you here. But we in general in science do not use pounds and inches. We use meters, centimeters. We use the metric system, and this is pretty standard now, and I've used it so often now that I have a pretty decent idea of how kilograms and weight weight in pounds translate from one to the other without thinking about the actual conversion. This data is cross-sectional. It's not one child followed on in their life. It's a lot of children at age 8, a lot of children at age 9, and so forth. So again, I just wanted to point out to you that these are the two that I'm going to be using, and these are when we say weight divided by height squared, we're talking weight in kilograms divided by height squared. Now, why do we take weight divided by height squared? Well, if someone's very tall, you would expect their weight to be pretty high compared to someone who's very short. So you have to factor out the influence of height on body weight to really get a measure of how different these two people are. And that's why we would divide by maybe height. But it's surprising that you would have to divide by height squared. And so the first person to notice this was a mathematician by the name of Quetelet, who was developing insurance tables. And he was the first one to notice that you have to divide by height squared. So just to give you a picture, I took all the CDC data and I plotted it as a scatter plot. Those are the dots that you're looking at here. And I plotted height on the x-axis and weight on the y-axis. And what you see is this kind of shape here. And it does look like it's curved. It doesn't look like it's a line. But I put a trend line in there just to show you that the R-square is pretty high, 0.57, which is really good for medicine. And this is the y equals mx plus b formula of this line. This is the best fit line in this data. But you can definitely see that this line is not doing a terrific job at accurately looking at this data. So it looks curved. The data looks like it has a curve shape. So what if we put the first curve we know about? A square. Well, you can see that it does look much better, and the R-square is 0.57. That R-square has indeed gotten better, and this Y stands for weight, and the X is height. So it does look like we do a little bit better with height there as height squared. So you consider weight as height squared. I tried a cube, I get a little bit better. And it does look a little bit better here as a function that approximates all this data. So the question is, how do we know for children that it's going to be height squared, height cubed, height to the 8th? We don't know these things for sure. Is there a way to really figure this out using mathematics without actually just guessing and testing and eyeballing it? So that's what I'm after. I'm after a way that I can find the best power, squared, cubed, or whatever, using math. So what I'm really saying is, if I know that weight is equal to some constant times height to a power, is there a way to find what that power is going to be, the best power is going to be? Is it going to be squared? Is it going to be just height alone, height to the 1 power? Is there a way that I can calculate it by using the data? And the answer is yes. I need to use logs and exponentials. A log is the inverse of an exponential. It is what undoes an exponential. Just like square roots sometimes undo squares. So if you want to find, if you have x squared, when you want to undo that, you take the square root. Just like a reciprocal undoes the original, just like a minus sign undoes the plus. So this is what inverses do. They undo the function at hand. So that's the way you should think of inverses, because that's how we use them. So what is a log? It's the inverse of an exponential. For example, if I have 10 squared equals 100, then log base 10 of 100 is 2. It's the undoer that gets at this 2 here. It considers the 2 as the variable that I want to isolate if I wanted to get this equation undone, and that is exactly how it's used. And that's the relationship I had memorized from my high school teacher years ago. He'd always give us this 10 squared is 100 and log base 10 of 100 is 2. That's the relationship between logs and exponentials with real numbers in them. So this is the formula they give you in pre-calc textbooks. If you have b to the x is equal to y, b stands for base, then log base b of y is equal to x. That's the relationship. So this, if you log base b both sides, you would get that x isolated. That's the purpose of it. I never remember it like that. I remembered it with numbers. I had a fabulous high school teacher, Mr. Wilkinson. He's on my Facebook, and he sometimes posts on there, and he taught us to think of this in numbers, and it's much more memorable that way. So that's the purpose. It allows you to solve for x when x is up there. Well, what is it I was wanting to solve for up here? I wanted to solve for the p. I wanted to solve for the p. So that you can see where I'm coming from here on this real application. There's two popular bases that we like to use. Usually it's not two. One of them is log base 10. In biology and medicine, they always use log base 10. And you'll see this in medical textbooks, and you'll definitely see this in your bio textbooks. And I did see it also in the chemistry to PChem textbook when my sister was taking PChem. So it's used in the life sciences and chemistry. In engineering and math, we usually use the base e. And somebody asked me, what is e? Well, e is a number, a special number like pi, and I can't tell you yet what what's really cool about it, but it shows up in the strangest places, and it's a really, really interesting number. But like pi is 3.14159 dot 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 has this infinite expansion. E also has an infinite expansion. It's around 2.718 dot dot dot. It just keeps going forever. So it's this special number E named for a German mathematician named Euler. E is what I just naturally use. I didn't think about this until someone said it in class, but I use E all the time. I think E is really cool, and I'm used to using it. When we say ln, no, I just naturally use it. This is called the natural log. This is the log base E, when E is the B, when I had that formula before. And it's special. It got its own little ln. All the others are log base B. This one has, we don't write log base E, we write ln. It got a special little tag. So it's a pretty big deal. The 4 log laws on your quiz are that the log of x times y is the log of x plus log of y. Second one is log of x divided by y is log of x minus log of y. The third one is log of a to the n is n log a. That's the important one. I'll show you in a second why. And finally, that log of 1 is always 0, no matter what the base is. Notice I don't have a base here on any of them. It could be base 10, it could be base E, it could be base 2. All these log laws hold no matter what the base is. So I'm going to put the third one here. It's the most important one, at least to me. This is not the only application of logs, but it's what we use logs usually for, or what I've seen it used usually for. I'll tell you in a second another thing that I know that they use it for in biology. But here I'm just going to log both sides because, again, I told you I want to go after p. So if I log both sides of this equation, I get this. And by log law number 1, it splits up as a plus. And by log law number 3, the p comes out in front. And now I've isolated p. In fact, I've written, if I consider log of w as y, then the p is my unknown, that's the slope. And if I consider log of h my x, and the log of m my b, I'm really looking for the equation of a line. Instead of the original w, I take the log of the w, and those are my y values. And then I take the log of the h's, and those are my x values. And for about 50 years, that's how people have been finding the best scaling exponent, the best exponent. And this scaling exponent thing, it's not just in medicine. It shows up in all kinds of areas like physics. So this is how people look for the scaling exponent. So that's just one application where logs are really important. Logs are also used in biology. I've seen it used, and also physics. I've seen it used when your numbers get really, really big. So you log transform the numbers and you make a log plot so that you can see it in some reasonable squished way. You can see what the trend is without having to look at the large y values on your graph. That's another application of logs. Your pH values that you use in biology and chemistry are actually log transform numbers. So they are made smaller. And they're log base 10. So now let's go to your quiz problem from WebAssign. I'm sorry you had to listen to that from me, but I told you before I started the class that everything is relevant. So I'm not going to show you, I'm going to get irritated if I have to show you something that's not relevant. This is, after all, calculus for the life sciences. So let's look at your quiz problem from WebAssign. It was to find the inverse of a function that had e's in it, like this. The first step is to write it as y equals e to the 2x minus 4. What you are going to do is you're going to solve for that x. That's what you want to do. You want to isolate that x. So you're going to ln both sides. Why will you use the natural log? Well, because your base is e. So that's why you're going to use the natural log. If the base was 2, you'd log base 2 both sides. But now I have to log base e both sides, which is ln. So ln y is equal to ln of this mess right here. Log law that says that I can factor out the exponent to the front, I'm going to apply that law. So that's my a and that's my n in log law number 3. So that exponent comes out to the front, and that's where I'm at. Now, log base e, natural log of e is 1. If you have log base b of b, it's always 1. So that is a fact that you have to either remember or punch on your calculator to be reminded. But it's really important. It seems to show up every once in a while in fake problems. In real problems, I rarely get something so nice. But let's go back to the fake. So that gives me that log of y is 2x minus 4. And now I can solve for x using Math 100, Red Hawk, Learning Center math. Here we go. 2x minus 4 is natural log y. I add the 4 to both sides. And then I don't like to divide. I just don't like to, because in calculus often you want to have things separated. So instead of dividing both sides by 2, I multiplied everything through by 1/2. So if I multiply everything through by 1/2, I get x is equal to 1/2 natural log y plus 1/2 4. And so that's where I'm at. That's my formula. If you want to get it WebAssign ready, this is the inverse. This is how I solve for x. WebAssign ready, they want everything swapped around. The inverse function, swap the x's and y's, is 1/2 natural log x plus 2. And that's the inverse function. And that's how you do it. So you will have a problem on the test on the quiz like this Monday. You had a problem on WebAssign, your first WebAssign like this. Just let me know if you have any questions about this.